for anything for a century, never mind hundreds of centuries. So the idea is that algorithms do have a finite time, but that time is not bounded by anything specific. You may find out that some algorithms run a very long time. I'll give you an example. There is an algorithm which has an exponential complexity. We're going to look at this algorithm, and the complexity of this algorithm is 2 to the nth power, where n is the problem size, 2 to the nth power. So the question is, how long will it take my computer to solve that problem? Well, let's make a supposition. Suppose I can execute 1,000,000 instructions per millisecond. If I can execute 1,000,000 instructions per millisecond, how many instructions can I execute in a second? 1,000 million, which is 1,000,000,000. So let's suppose I can, now we're talking about billion instructions per second in terms of gigahertz, but when I'm talking about billion instructions per second, let's suppose I can execute 1,000,000,000 high-level instructions, not machine instructions, which are simple and fast, but high-level programming logical instructions. So if I can execute 1,000,000,000 of them per second, suppose I'm trying to solve a problem, and the problem has a complexity, I'm going to put it out here on the margin, hopefully this pen writes, of 2 to the nth power. That's the complexity. And again, I'm just trying to give you an example. So in this case, let's say n is equal to 64, which is not a huge number, but when it becomes an exponent as part of 2, it is a very substantial number. And I am executing now these instructions at a rate of 1,000,000,000 per second. The question is, how long will it take you to finish? Because it's an algorithm, so it's going to finish when the instruction is finished. That's the finite value here. And at that rate of speed, that algorithm would take you to execute until completion approximately 3.61 times 10 to the 61st power centuries. Centuries. 3.6 times 10 to the 61st power centuries. So effectively, we can't solve this problem even though there's an algorithm. So just because an algorithm exists, if that algorithm has very, very low efficiency, it may not be practical to run this algorithm. We may need to find a better algorithm, or we may decide there is no better algorithm. But how can we do that? How can we decide there's no better algorithm? How can we decide that? What if somebody tells you, okay, I need you to in your job, you need to write a program that's going to solve this particular problem for me. This is the problem. I need you to do this, and I need this. Please finish it over the weekend. Oh, great. Okay. So you literally spend all weekend trying to solve this problem, and you cannot solve this problem efficiently. You can solve it, but your algorithm is taking so long that for the size of the problem you need to solve, it's not going to be practical. It's not going to be useful. So you come in the morning, your head is down, it's like, I failed to write this algorithm. I have a way of solving it, but it will take, 2 times 10 to the 45th power centuries on the fastest computers that haven't been invented yet, so I guess I'm a failure. Well, maybe you're not a failure. Maybe you're not a failure at all. Maybe the complexity of the algorithm is very, very high, and maybe, just maybe, there is no way of creating a better algorithm known to the current humanity as represented by the best computer scientists, best mathematicians of all time. How could you do that? How could you say, I couldn't find a solution, but neither could these 500 mathematicians and computer scientists. They couldn't find an answer either. Well, how could you make that statement? Well, you can make that statement if the algorithm, if the problem you're trying to solve could be mapped directly onto other problems that have been determined to be very hard problems, so-called hard problems. If your problem essentially can be transformed into that problem by some algorithmic technique, if that problem that you translated onto was not solved efficiently, only has a very bad complexity solution, then in a sense what you're saying is our problem is equally hard. It belongs in that class, therefore we can't solve it efficiently. Nobody has done it yet. Nobody has done it yet. And there are such problems. There's a very strange question in computer science. It's the question in computer science that you will get lots of money for if you can answer it, if you can prove one way or another the following. So algorithms fall into two broad categories. We can divide them into, the first group is called P. And the second group is called NP. P and NP. P is the set of algorithms for which there exists a polynomial time solution. Polynomial means like linear or quadratic, second power, or cubic, third power, or quartic, fourth power, or fifth power. If there is a polynomial algorithm for a particular problem, then that problem falls cleanly into the P problems. And P is a set of problems that can be solved in polynomial time. But some problems don't fall neatly into P. They are the kind of problems is that you go do the first step, and then there's a polynomial way of solving them, but unfortunately there's another choice, which is polynomial. And wherever you go, there becomes another branch that's polynomially hard. So we have an incredible explosion of polynomial complexities that comprise the solution of the problem. So NP represents those problems. Those problems are called non-deterministic polynomial. It means I can go left and it will be a polynomial complexity, but there's it's not a certain solution. So now I can go another way, which presents two more possibilities, and each of them can be polynomial, but there's no guarantee. And as you go, they keep splitting and splitting and splitting. So these polynomial solutions are simply multiplying by themselves without end. And they basically approach these exponential problems, complexities. So we know exactly which problems fall into P, because those are the problems for which we know algorithms that solve them. We also know exactly which problems definitely fall into NP. So right now, we view them as a disjoint sets. These are P, these are NP. There is a division bar between them. They're split. There's no connectivity. Now here's the open question in computer science. Well, here's the challenge first. The challenge is, can you find a problem that's currently in the set of NP problems and find a polynomial algorithm for it? If you do, you will win the Turing Prize. The Turing Prize is, I think, over $1 million right now. You'll also be extremely famous, and you will change computing as we know it. It's pretty cool. So it's a big challenge. That would happen if you could solve one NP problem and put it into P. Nobody's been able to do that. So let's make the challenge a little bit smaller. Let's prove that the P problems and the NP problems are actually different from each other. Meaning that a problem in P and NP are different. No problem in NP can cross over into P because there is an inherent basic difference between the problems. So the challenge is prove that P does not equal to NP. And nobody's been able to do that. On the other hand, maybe we can be revolutionary and say, you know something, these NP problems, nobody's really considered certain ways of solving them, and I can find ways of translating these problems into P problems. And if I can translate them into P problems, I can solve them using polynomial time algorithms. And nobody's been able to do that. So the open question in computer science is the question, does P equal, question mark, NP? Are those in fact the same set, but we just can't distinguish it? We can't prove that they're the same set. We can't prove that they're disjoint sets. Computer scientists largely and mathematicians believe that P does not equal to NP, but no one has been able to prove it. And that's also worth the Turing Prize, if we can prove that they are actually different problems. They're different problems. So people have spent their careers sometimes considering these problems and trying to show the sameness or the difference, and nobody's been able to do it. So the interesting thing about the NP problems is that there is a subset of the NP problems called the NP complete problems. NP complete problems. And the NP problems are NP problems. But they're a special subset, so they are still NP problems, but they're NP complete. Because, and there are hundreds, if not many, many more problems in NP complete. The cool thing about them, they're all different problems, but they're all NP, hard, but they're called NP complete is because we figured out how to transform one of them into the other. Meaning that if we find a problem that can be transformed into an NP complete problem using a polynomial time algorithm, then that problem becomes a part of the NP complete set. Which means that if I can solve the NP complete problem and transform mine to the NP complete problem, then I can solve mine the same way. So the cool thing about that is if you can solve one of those NP complete problems, because they're all transformable into each other, you've solved all of them. And some of the NP complete problems will, all of them will revolutionize computing, because it will take problems that are effectively impossible to solve in real time. Algorithmically, yes, but not in a practical time, and turn them into problems that we can solve almost immediately. So that's the cool thing. That's the open question in computer science. That's the open question in algorithms. I don't think we're going to resolve that question necessarily in this class, but it's important to be aware of that question and to be aware that such problems exist. And I will show you a couple of problems and say, well, these problems are real problems and they come up in computer science all the time. And we have to solve them. So how do we solve them? If the algorithms are going to be so inefficient, they're going to take centuries, we can't depend on that kind of solution. So we may have to have other solutions, other approaches to solving problems. And that's sort of where deep thinking and deep learning comes into, and artificial intelligence and neural networks. These are systems that are not necessarily algorithmic directly for the problem, but there are ways that we can get good solutions. And then another question comes in, is it really important if I have a problem that's extremely complicated? Is it really important for me to find the best solution? Or is it really important for me just to find a very good solution? Isn't that good enough? See what I'm saying? So there are other techniques of solving problems other than algorithms. I don't think I have them up here. But typically those type of techniques are called heuristics. I'll write it out because it's a funny word. Heuristics. So the H is silent. And a heuristic is not an algorithm. It's essentially a set of steps that tends to get you to a solution. So a heuristic is an approach that tends to get you to the right solution. But it doesn't guarantee an optimal solution, and it also doesn't guarantee a finite number of steps. It could go infinitely. So you could be basically always converging on the best solution, getting closer and closer and closer, and more than likely you're going to get stuck somewhere before you get to the final solution, but it may be very, very good. And so there are some very exceptionally good heuristics to very hard NP problems. And there are proofs which are remarkable. We're going to be talking about proofs in a minute, but there are remarkable proofs. A proof is something that's irrefutable. We can show it, we can argue it logically, and demonstrate its fundamental truth. That's what a proof is. there are proofs that say, here's a problem, and I can't, in human time, get the optimal answer. I can't. Not for a large problem. But I have a polynomial-bound heuristic that will solve the problem to 90% of the optimal answer, even though I don't know what the optimal answer is. That's called a remarkable proof. You're saying I can solve, guarantee at least 90% close to the optimal answer, even though I don't know what the optimal answer is. Now, that's a proof. That's a proof. So, these are big things. I kind of throw them out there for you to think about, a little bit of a backdrop on what we're going to do, and then we're going to get small again. We're going to get much more concise, much more specific to what we're going to do here. Okay, let's go back to our question. So algorithms is a finite series of steps, solves a problem that always works. Now, if the algorithm is very simple, we may not need convincing other than we'll look at it. It's obviously going to do it. It's obviously going to work. But some cases the algorithms are not so simple. It's like, well, I'm not sure if it's going to work. And I need to implement this on a large scale in a company. Our reputation depends on it. Our success depends on it. So I don't want to implement it until I'm certain that this algorithm is really going to do what it's going to do. So you may then require verification, and the verification is a proof of correctness. So proof of correctness is a verification that an algorithm, in fact, does what it purports to do. It actually does it. So the proofs are useful, especially for these non-obvious algorithms, the algorithms that are not simply obvious. Like, oh, I can see. I was like, of course it's going to do that. So if you have a more complicated algorithm, that's what I'm talking about. Sometimes when you go through a proof for one algorithm, you are going to expose a strategy which is inherently part of the properties for the algorithm construction. So you learn by proving an algorithm, you learn the underpinnings, the underlying fundamental way that the algorithm is constructed. What does it give you? It gives you power because it gives you a knowledge of how algorithm construction works. Also, by proving you can compare against other algorithms that may be similar or contrast in algorithms that do things differently. Gives you understanding. And once you understand all that stuff, of course, naturally, it enables you to better develop future algorithms. You get it. You understand how it works. So let's get specifically to the type of proofs that we're going to be using that are important to us in this class. And one of them is called a direct proof. So direct proof, basically, let's read the statement here. Prove P, and then this little arrow we read implies Q. Prove P implies Q. If you prove P implies Q, what you're doing is you're proving that P implies Q is true. That means there's a truth value to P implies Q. There's a truth value. P implies Q. That can be proved to be true, or it may be proved to be not true. But what is P and Q? Well, P and Q are simply statements. So P is a statement, and Q is a statement. And statements also are either true or false. So P may be true, Q may be true. In that case, P implies Q may be true. So there are three truth values here. One is for P, one is for Q, and one is for the whole thing right here. And P implies Q, we call that an implication. Implication, because P implies Q that's the implication. P implies Q. So how do we prove that P implies Q? Well, the first thing we do, we assume that P is true. Because P implies Q can also be read as if P, then Q. If P, then Q. P implies Q means that if P is true, Q is also true. So therefore, to prove that that's the case, then we will assume that P is true, and then we will use rules of inference, logic, to show that invariably, always, every single time, Q must always follow to be true. So if we start with P being true, then Q must be true automatically. And we use logic and inference to show that this is true. In case of mathematical proofs, we can use mathematical theorems, mathematical postulates, anything that's mathematically valid we can use to prove something. So, indirect proof, you want to prove, again, P implies Q. If P, then Q. But it is more convenient for us to prove sort of the negation of it, which is that not Q implies not P. In fact, logically speaking, we can show that not Q implies not P is exactly logically equivalent to P implies Q. So if you can prove this is true, you have also proven that this is true by logic. And how many of you have had this type of logic? Either in sociology, sometimes you have it, or in mathematics. Anybody seen this before? Some of you, okay. So in this case, if we're going to prove this to be true, then we will start with not Q, assuming that not Q is true. And then use the rules of inference and logic to show that the conclusion, not P, is also true. So let's think about it. Let's do a simple example. Let's say P is a statement, and the statement is today is payday. Everybody likes payday, right? Yeah. It's better than not payday, right? Okay, so today's payday. Today's payday. And Q is I am happy. So P implies Q means if it is today's payday, then I am happy. We'll modify the statement slightly. If today's payday, then Professor Dichter is happy. We'll make it about me. All right? So that's fine. So what happens? So if today is payday, then I'm happy. So all of a sudden, you're coming into the classroom, and I'm like very happy. So you're thinking to yourself, I wonder if it's payday. So you're thinking it's probably payday. You're thinking, if he's happy, it's payday. But the implication says, if it's payday, I'm happy. So you come up to me and say, Professor Richter, I heard it's payday because you're so happy. No, it's not payday. So does that mean that the implication is false? No, actually it does not mean the implication is false. Because the implication is, if it's payday, I'm happy. There may be other implications that also make me happy, right? If it is a sunny day, Professor Dichter is happy. But if I'm happy, I can't produce a sunny day. And if I'm happy, I can't produce payday either, right? So you know that if it's payday, I'm happy. You don't know that if it's a sunny day, I'm happy. So we cannot go backward, because going backward would be Q implies P. Happiness implies payday, and it doesn't. It doesn't. So therefore, if we're going to prove this is to be true, then we must assume that it's payday and follow all the logic to show that I'm happy. And of course, that's not possible to do in this example, but we'll have some mathematical examples that are much more clear. Okay, any questions on direct and indirect? They are really the same, but sometimes it's easier to do indirect to try to prove P implies Q. Okay, then we have two other proofs that are much more powerful and much more useful to us in many cases. One of them is the inductive proof, and the other is proof by contradiction. Yes?
Can you explain indirect one again?
So, let me show you. Okay, in this example, I'm going to use the board. Okay, so we're going to use the board. And like I said, this is kind of a bad part of the, let's see if I can move everything up a little bit. That's it. Okay, so this is very simple. So we have a chart. Okay, so here I'm going to have P. And here I'm going to have Q. And here I'm going to have P implies Q. P implies Q is an implication. It's true whenever, if P then Q. So now P and Q are statements that are independent from each other. Therefore, each of them can be true or false. There are two possibilities here, two possibilities here. So each of these two have two, creating a set of four. So of course, we're going to have something like this. True, 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 false, false, true, false, false. So those are the values for, logical values for P and Q. Those are all possibilities. We're trying to prove if P then Q. If P, then Q. Yeah. Yeah, because P is true and Q is true. So in that case, if these are both true, then the implication would be true. However, here, notice that P is true, but then Q doesn't follow to be true. Therefore, the implication is false. And in the last two ones, notice that P is false to begin with. P is not even true. But the implication says, if P, then Q. If P, then true. If P is true, then Q is true. Well, P is not true, therefore the implication is not addressing this issue. So therefore, we are not contradicting if P, then Q. And not contradicting it defaults to being true. So the implication is true whenever P is false. So you can see that these are the values of the implication based on P and Q. Now, if you look at not Q and not P, then of course if Q is true, then we just negate it here. So that's going to be true makes false, false makes true, true makes false, false makes true. I just negated Q. To negate P, we're just going to put a not in front of it, so that gives me true, true gives me false, false, and this gives me true, true. So now I will look at not Q implies not P. Not Q implies not P. What's the value here? True. True. What's the value here? This is going to be false because we have true implies false. No, that's false. Then here false implies true. That's true. And true implies true is true. Notice that the values here are what? The same. And because the values are the same, the indirect proof and the direct proof are equivalent to each other. So if you want to change, so if you want to prove if today is payday, then Professor Dichter is happy, then you can prove if Professor Dichter is not happy, then it is not payday. Those are equivalent.
Thank you.
Yes. Sorry. Let me repeat that. I said it incorrectly. So to get the indirect, the direct is if today's payday, Professor Dichter is happy. If Professor Dichter is not happy, it is not payday. I'm not sure if I said it correctly. If Professor Dichter is not happy, it is not payday. Why? Because if it's payday, I'm happy. So if you see I'm looking miserable, it can't be payday. Because if it was payday, I have to be happy because the implication is true. Okay. Does that make sense? Does that answer the question a little bit? Okay. Okay, so now we're going to look at the inductive proof. Inductive proof is a proof where you are trying to show that something is true in all cases. A statement is true. So for example, the statement is true when some variable is 1. The statement is true when some variable is 2, and 3, and 4, and 5, and 10, and 1,000, and 1,000,000, and 1,000,000,000, and forever. So of course it's very easy to prove something if you know the value is 1. Because you can just plug it into the statement and find out if it's true or false. But that takes time. And then you can prove it for 2 and prove it for 3. But how do you prove it for all positive values, for example? How can a statement be true for all positive values? So we can prove it by showing that P, which is a statement, is true when the parameter is 1. And that's a basis. That's a beginning, basis. So we prove that the statement is true in the first case, the base case. We assume that P of j is true as j is more than 1 and less than some value n, some general value n. We assume it, and then we show that based on the assumption, P of n must also be true. Now that's a very slippery idea. Proof by induction is a very slippery idea. Because how can you prove something is always true when you're working off an assumption, Pj is true for all values greater than 1 and n? Well, we know greater than 1 because 1 has already been proved directly. We show that directly. That's called the basis. And this one we assume, and based on the assumption, we prove that it's true generally. How can we make that statement? So I will show you how induction works by applying it, but I will also prove to you, that induction is a valid proving technique. Because you should be a little bit doubtful, but you need to have complete confidence in induction. But how can we prove the inductive process works? Well, we'll get to that. So the next thing we're going to look at is proof by contradiction. Proof by contradiction is also a very powerful technique. We want to prove that something is true. And we do it in just the opposite of how you would think we do it. We want to prove that some statement P is true. So we start by simply assuming that P in fact is false. And if P is false, there are some things that automatically hold true. When something is false, you can say, well, if it's false, then this also follows, and this follows, and this follows. Right? For example, if it is raining, then it follows that there are no shadows on the street. You know, assuming no lamps, street lamps, in the middle of the woods. If it is raining, then we're going to have no shadows. We're going to make some assumptions. So whatever we can assume from a given is useful for us. So we want to show that P is true. But to show it, we assume that it's false, and then we take the consequences of what it means for P to be false. So we make these inferences with the assumption that P is false. We put these observations and facts together to show that it leads to a contradiction that P was false. The assumption that P was false led to a bunch of facts which pointed to the fact that P cannot be false. And if P cannot be false, then P is true. So when we come to a contradiction, this implies that P must in fact be true. Okay, so let's take a look at some examples, because these are... So let's take a look at this example here. So we're going to look at an example here of a direct proof, and also one which is going to be an indirect proof. So this should make it a lot easier to understand. So we want to prove that if n, some integer, is odd, then n squared is odd. If n is odd, n squared is odd. Okay, that's what we're going to try to prove. So, well, I can think about it. First of all, is 1 odd? What's 1 squared? That's odd. Okay, 3 is odd. What's 3 squared? That's odd. How about 5? 25, yeah. How about 7? 49? How about 1,111,237? Okay, we don't know what that one is. So we cannot try them all, can we? We cannot try them all. So we're going to have to look at a technique. So what we're going to do is we're going to say, let's assume that we have an odd integer. So from number theory, we can say if n is odd, if n is an odd integer, then n can be written as 2 times an integer k plus 1. Every odd integer can be written as 2 times an integer k plus 1. So for example, when k is 0, what's the integer? 1. When k is 1, we have 3. When k is 2, when k is negative 1, negative 1. So every odd integer can be written as 2k plus 1, where k is any integer. Because if k is an integer, 2 times k must make an even integer divisible by 2. Adding 1 to it makes it odd. And we can get all the integers. So number theory allows us to represent n as an odd integer in 2k plus 1. Where k, this is notation, is an element of z, and z is the set of integers. So since 2k plus 1 is n squared, another way of writing n squared, let's square n. When we square n, we get n squared. When we square this representation, we get 2k plus 1 squared. And that, of course, produces the binomial square of 4k squared plus 4k plus 1. So now, this is n squared. We need to show that n squared is odd. To show that n squared is odd, we're going to try to put this trinomial into an even plus 1 format. So we take that 1 out, plus 1, and then we try to factor out a 2 here. And a 2 out of this is going to be 2 times 2k squared plus 2k. So you can see here, again, integer, integer. So this is going to be an integer plus an integer times 2 is an even integer plus 1 is an odd integer. That's the proof. So again, direct proof, if it's odd, then it could be represented like this. Square it, and then factor it using factoring and arithmetic to show that we produce an odd number every single time. So now we know every odd squared is always odd. We proved it for all, but we didn't have to plug everyone in. Okay, so the second one, we're going to try to do a similar proof, but it's going to be a little bit different because it won't be as convenient to go direct. So we want to prove if 3n plus 2 is odd, then n is odd. But that's funny because 3n plus 2, how do I make 3n plus 2 odd? There'll be an awkward way to represent. So what I can try to do is prove p implies q by proving not q implies not p. That's what we did under there when I showed you those truth tables. So therefore, not q is n is not odd. Not odd means what? Not odd means that it's going to be even. So we're saying if n is even, then 3n plus 2 is not odd. It's also even. So what we're going to prove is, to prove this, we can prove equivalently, if n is even, then 3n plus 2 is even. So if n is even, that's our not q, then n can be represented by number theory 2k, where k is an element of the integers. So again, if k is 0, it is 0. If k is 1, it's 2. If k is 2, it's 4. If k is negative 1, it's negative 2. Negative 2 is negative 4. So this is the representation of an even integer. So we're going to take that integer, and then we're going to take that integer, multiply it by 3 times 2k plus 2. And the result here is 6k plus 2, and we want to make that even. So to make it even, what we're going to do is we simply can factor out a 2 from both parts, and it's going to be 2 times 3k plus 1, and 3k plus 1 is clearly an integer, multiplied by 2 is even. So we have proven R. Okay, questions about either of these? Make sense? Not too bad. Okay, so sort of in addition to direct proofs are biconditionals. A biconditional is one of these things where basically you want to prove that P implies Q, but notice that the arrow goes from P to Q, but it also goes from Q to P. When you see this, we read it as if P then Q and if Q then P, or we read P if and only if Q. P if and only if Q means that we have a direct proof from P to Q, and we have to have a direct proof from Q to P. So this is different than what we had before. So to prove this is true, you need to do 2 direct proofs, from P to Q and from Q to P. Of course, you can do indirect proofs. You can say not Q implies not P, and not P implies not Q. That's equivalent. But you have to break it down somehow. So we read this by if and only if. So let's say we have a triangle with the sides of length A, B, and C. And the statement is a squared plus b squared equals c squared if and only if the triangle is a right triangle. Well, if we have that statement, what it really means is that there are 2 direct implications. The first implication is a squared plus b squared. If a squared plus b squared equals c squared, then the triangle is a right triangle. But the other one says Q also implies P. If the triangle is a right triangle, then the sides a squared plus b squared equals c, then the sides a squared plus b squared equals to c squared. And so we have to prove it. Essentially, proving a biconditional, you just have to do twice as much work. Because you gotta go both ways. If I said, if today is payday, or if it is payday, if and only if it is payday, Professor Dichter is happy, then that means if I'm happy, it's payday. If it's payday, I'm happy. If and only if. Nothing else. So, if the triangle is a right triangle, then the Pythagorean theorem can be used to show that a squared plus b squared equals c. I'm not going to give you the Pythagorean theorem. I hope you remember a little bit of Pythagorean theorem, right? That's what it ends up with, a squared plus b squared equals c. So therefore, if the triangle is a right triangle, then a squared plus b squared equals c squared. That is proved by the Pythagorean theorem. And of course, if there is a well-known theorem, we can just cite that theorem since it's already been proved in Greece by Pythagoras. Now, in a triangle, we have something called the law of cosines. And the law of cosines looks like this. C squared equals a squared plus b squared minus twice these sides times the cosine of the angle facing the C. That's the law of cosines. If you don't remember it, it's not the end of the world. I'm not going to ask you about this again. But I'm just showing you that it can be. So there is the law of cosines. And the law of cosines basically is a generalization of Pythagorean theorem. Pythagoras didn't figure it out. Later people figured it out. But he figured this part out. But later people said, well, you can generalize it. So actually, if you think about it, if u, which is an angle, if that angle has 90 degrees, what's the cosine of 90 degrees? Do you remember that? So cosine 90 degrees. It's 0. Well, the cosine of, so if the angle facing C is 0, it's 90 degrees, then cosine of this is 0, and all of this is 0, and c squared equals a squared plus b squared. So because the law of cosines uses the cosine of an angle facing C, only when the cosine is 0 does this formula become this formula. So therefore, a squared plus b squared equals c squared if and only if 2ab times cosine u is equal to 0. 2 cannot be 0. A is the length of a triangle, cannot be 0. B is the length of a triangle side, cannot be 0. So the only thing that can be 0 is cosine of the angle. And the only cosine that has a 0 is going to be 90 degrees. You say, wait a minute, what about 270 degrees? Can't be a triangle. The only angle in a triangle that has a 0 cosine is 90. Because the triangle has to have 180 degrees total, so you can't go to 270. So that's the only possibility. Does that make sense? Okay, so this is biconditional proof. Any questions about biconditional, direct, indirect? All right. All right. So let's take a look at this example here. So this is going to be an inductive proof. Inductive proof, proof by induction. So what we want to do is we want to prove that the sum no, I'm going to actually, let me just do this on the board. I think it's more exciting on the board. This is fine, but I want to do it on the board. So let me do that. Oops. Just doing it really times. I guess I have to turn it off, which is bad, but that's what I do. Okay. This will give me something to do. I need a little board time. So we have the sum, and we have, I'm going to say here, let's just use I goes from, I'll just copy from here, from 0 to, I can use a 0 to n of 2 to the I. So let's make sure we get the right answer here. Is equal to 2 to the n minus 1. Right?
No, I mean the sum should be minus 1. I equal to 0 to minus 1. It's just shown on the board.
Let me just think for a second. Yeah, you could be right. Let me just think for a second. Everything's correct.
No, it's just shown on the board.
Huh?
You said show on the board is from I equal 0 to n minus 1.
Well, this is going to be, for this one, it's going to be 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus, let's say, 2 to the 4. Let's say n is equal to 4, okay? So the value here is going to be 1, 2, 4, 8, 16. This is going to be 15, right? So I think you're right. So it's going to be 31. So it should be n plus 1. That would work, right? Or we could go n minus 1 and then we can have n. It's okay. Because then the sum would be equal to 15. Okay, so you're right. Thank you very much for that. Okay, I would have checked it out, but thanks for getting that. So we want to prove this. Prove by induction. Okay, so there are 3 steps in a proof by induction. The first step is called the basis. So basically, notice that we are letting I vary from 0 to n minus 1. Okay? So the basis is when n is equal to what? The basis, so our value of n is completely general. So what's the first value? We want to have a single term in the summation. So a single term in the summation is when I goes from 0 to 0. So if I goes from 0 to 0, that means that n minus 1 must equal to 0. So n must equal to 1. So the basis is n equal to 1. Because that gives us one term. So what we're trying to do, so we're trying to prove initially p of 1. Remember how we did the p of 1, p of 2, p of 3? We want to prove it for all values. So p of 1 is, we can do this directly. And to do that, all we need to do is plug directly into here, and we have the summation as I goes from 0 to 0. So the summation as I goes from 0 to 0 of 2 to the I is equal to, there's only one term, 2 to the 0 is equal to 1. Correct? That's just mathematics. From 0 to 0, there's one term in the summation. 2 to the 0, by definition of 2 to the 0 power, is equal to 1. Now we want to find out whether it's equal to this. So this is the left side, this is the left side in here. And now we're going to have the right side, and the right side is going to be n is equal to 1. What's 2 to the 1? 2. So this is going to be 2 to the 1 minus 1, which is 2 minus 1, which is equal to 1. So notice that the 1 and the 1 are the same. So all we've done here is basically verify that the basis is true. That's the easiest part. Plug in the first value. What we're trying to do is we're trying to prove for n equal to 1, 2, 3, 4, forever. That's our goal, is to prove for all positive integers n. So the left side is simply an expansion of the summation with the particular n value. So 0 to 1 minus 0, 1 minus 1 is 0, 0 to 0. 2 to the I is a single term, is equal to 1. And the right side is an expansion of the right side with the substitution of the n parameter, which is equal to 1. So 2 to the 1 minus 1 is equal to 2 minus 1 is equal to 1. So we've checked that these two are the same. Therefore, it is true when n is equal to 1. So now we're going to go to the next step. The next step is the assumption. Now, before I go to the assumption, I want to make just an observation. If we plugged in the value, the initial value, into what we're trying to prove, if the two values on the left and right side did not agree with each other, they were different, then guess what? You have disproven it. The proof is done. It's false. If the basis is not true, it's false. Period. You finish. You don't do any more than that. So if I give you an instruction, prove or disprove, then if you can disprove it at this stage, you're done. If you can't, you need to proceed to see if it's proved. Remember, it's always easier to disprove something than it is to prove something. Because to disprove something, all you need to do is find one exception to